Welcome to the deep dive. Today we're plunging into, well, a truly foundational document of modern physics. Erwin Schrödinger's collected papers on wave mechanics.
A cornerstone, really. It's hard to overstate its importance.
Absolutely. And our sources for this deep dive are specific excerpts from the 1928 English translation of Schrödinger's groundbreaking German papers. Our mission basically is to cut through some of that original scientific density,
Yeah, it can be pretty thick going.
and extract the most important nuggets, help you understand the very beginnings of wave mechanics and its, well, pivotal role in the early quantum revolution.
And this collection, it isn't just some dusty historical artifact. I mean, it represents a massive shift in how we even approach reality.
A whole new way of thinking.
Exactly. It gave us a wave-based alternative, and that just profoundly reshaped physics. A lot of the core ideas are still absolutely central today.
It's always fascinating, I think, to get the human story behind these huge breakthroughs.
Oh, definitely. They don't just spring fully formed from equations.
Right. They come from real people, with lives and interactions. And Schrödinger himself gives us a little glimpse in the preface to the first German edition. This is from November 1926.
Okay.
He tells this wonderful anecdote, actually, the idea to gather his separate papers into one volume.
Yeah. Where did that come from?
Apparently it was sparked by a young lady friend, as he puts it.
No way.
Yeah, who apparently remarked to him something like, you had no idea that anything so clever would come out of it, had you?
Huh. That's fantastic. Such a human moment.
Isn't it? And he goes on describing how his ideas evolved. Started simply, he says, and then developed more and systematically.
So an iterative process.
Totally. And what's really striking is his humility. He admits right there in the preface
What does he say?
that it was, quote, impossible at the present stage of giving a firm exposition which would be really satisfactory or conclusive.
Wow. Even Schrödinger himself.
Yeah, it just makes you realize even the absolute giants didn't have it all figured out instantly.
Absolutely. And that glimpse into his mindset is so valuable. It shows you the real nature of science, right?
Yeah.
It's often iterative, maybe even a bit messy.
Not just neat eureka moments.
Not always, no.
Yeah.
Even for something as foundational as wave mechanics, the inventor himself knew it was still developing, that he didn't yet have that final, conclusive framework.
It's a great reminder.
Such a powerful reminder that science is this continuous journey of refinement, not just perfect revelations.
Yeah,
Oh, and just a quick practical note on the translation for anyone looking at the sources.
good point.
The 1928 English edition we're using, it was translated by J.F. Shearer and W.M. Deans. But crucially, Schrödinger himself reviewed it.
Okay, so he signed off on it,
Pretty much.
which was vital for making sure those key German terms like eigenfunction,
Which means
proper function, and
This time.
eigenwert.
proper value.
Exactly, making sure those are accurately conveyed, keeping the conceptual core of his work intact.
Okay, so let's get to that core. At the heart of these papers is just a radical new way of seeing the universe. Completely radical for the time.
Let's really dig into the abstract, and that first big paper, Quantization as a Problem of Proper Values, Part 1.
Right, this is where it really kicks off.
So Schrödinger's initial way in, it was through this thing he called the Hamiltonian analogy of mechanics to geometrical optics.
A famous analogy, yeah.
He suggested that, kind of like how a light ray follows a specific path, a mechanical system also has a path, not necessarily in our everyday space, but in this abstract configuration space.
Which represents all the possible states or arrangements of the system.
Exactly. And this analogy, this famous comparison,
It directly leads him somewhere crucial.
right, it leads to a wave equation for mechanics, basically replacing the old classical rules.
A whole new mathematical foundation.
And here's where we get the really famous terms: proper values and proper functions.
Eigenvalues and eigenfunctions, as we usually say now.
Right, so the proper values, these eigenvalues, they get identified with the mechanical energy E, at least in macroscopic problems.
Okay, so energy levels.
Yeah. And the proper functions, the eigenfunctions, those are the actual solutions to his wave equation that correspond to those energies. They're like the allowed wave shapes for the system.
And he found they had to have certain properties, didn't they?
Yes. He specified they needed to be one-valued, finite, and continuous.
Which basically means they have to be mathematically well-behaved.
No infinities, no sudden jumps, just smooth, predictable waves describing reality.
Makes sense.
And interestingly, this proper value spectrum, the set of all allowed energies, It could have both continuous parts and discrete parts.
And that's the connection to quantum theory, right? That discreteness.
Exactly. That's where Planck's quantum of action H comes in. The discrete energy levels, the quantization that Bohr and others had talked about.
It just naturally emerges.
It emerges as a consequence of solving the wave equation under these conditions. It's not put in by hand anymore.
Which, if you connect that to the bigger picture, was just a huge paradigm shift.
Totally different thinking.
Yeah. Before this, you mostly thought of quantum stuff as, particles jumping between orbits, discrete jumps.
Right, the Bohr model kind of picture.
But Schrödinger proposed this continuous waves, this wave phenomenon that just naturally produced these specific proper values, these allowed energy levels.
So quantization wasn't an extra rule, it was baked into the wave nature itself.
Precisely. The wave equation predicted it. That was a revolutionary insight.
Incredible.
And the sources also mention how sometimes you get multiple proper values for the same energy.
Ah, like degeneracy.
Exactly, degeneracy, where different wave functions, different states, just happen to have the same energy level.
Okay.
And this also pops up when you apply the theory, like calculating the Stark effect. You can get split proper values there.
We'll get to the Stark effect later, but that just shows the richness of the theory early on.
It really does. It had nuance and predictive power.
Okay, so another really intriguing paper in the collection, the continuous transition from micro to macro mechanics.
Ah, yes, bridging the gap.
Exactly. It tackles a question that, physicists still grapple with today, right?
Definitely. How does the weirdness of the quantum world turn into the everyday world we see?
Yeah, quantum mechanics usually deals with tiny systems, discrete quantum numbers. How does that scale up to, a baseball or macroscopic mechanics?
It's the classical limit problem.
So the solution Schrödinger offered, it was pretty clever.
What did he suggest?
He showed that if you consider a wave group, or what he called a Gaussian error curve, basically a localized wave packet.
Like a clump of wave.
And you consider cases where the quantum number gets very large, then this wave packet starts to behave effectively like a classical particle executing the motion.
So classical particles are just sort of very localized quantum waves, in a sense, when things get big enough.
That's the idea he was putting forward. It's a way to see classical mechanics emerge from quantum mechanics.
And what's so fascinating there is Schrödinger's really elegant attempt to build this continuous bridge.
Not two separate sets of rules.
No, he suggested that the seemingly totally different behaviors of quantum and classical mechanics are maybe just two sides of the same coin.
Depending on the scale.
Depending on the scale and the size of the relevant quantum numbers. It's a really beautiful conceptual leap, trying to ground quantum mechanics in the everyday reality we actually observe.
That seems incredibly abstract, though. Conceptually beautiful, but how does it stack up?
Well, that leads us right into the next bit.
Right, because the mid-1920s, this period was just buzzing with quantum ideas. A real intellectual showdown was happening.
Absolutely. You had Schrödinger's wave mechanics taking off.
And at the same time, Heisenberg, Born, and Jordan were developing something completely different sounding. Matrix mechanics.
Two major competing frameworks emerging almost simultaneously.
So how did they relate? Were they rivals? Were they the same thing? That's the big question, isn't it?
It was the question at the time, and the core difference looked pretty stark on the surface. Well, Schrödinger's approach, as we've said, uses continuous wave functions, differential equations.
Calculus, basically.
Yeah. Whereas Heisenberg's approach dealt with discrete variables represented by these potentially infinite tables of numbers matrices.
So matrix algebra instead of calculus.
Exactly. It looked like a totally different mathematical language. The papers, Schrödinger's papers, explore this tension.
What do they say?
They note that the formal mathematical standpoint of Heisenberg, Born, and Jordan, the matrix mechanics, it finds its chief triumph, Schrödinger says,
Its main strengths.
in calculating things like the intensities of spectral lines and selection rules, polarization rules, stuff that was harder initially with just waves.
Okay, so matrix mechanics had some practical advantages for certain calculations.
It seems so. But the amazing insight, which Schrödinger himself actually proved,
Was what?
is that despite looking so different, the two theories were mathematically equivalent.
Wow.
Yes. The sources explain that while the formal identity might seem, quote, far-reaching, Schrödinger basically asserts that his wave equation, if you generalize it properly, it can actually produce the same results as matrix mechanics, especially for more complex non-conservative systems.
So they weren't competitors after all.
Essentially, no. They turned out to be two apparently equivalent forms, as the text puts it, for describing the same underlying quantum reality.
Like describing a house using blueprints versus, I don't know, a 3D model.
That's a great analogy. Different representations, same fundamental structure. And one might be more convenient for certain tasks, calculating the plumbing versus visualizing the facade.
Okay, that makes sense. But science isn't just elegant math, right? It has to match reality.
Absolutely. The ultimate test is experiment.
And Schrödinger definitely put his wave mechanics to the test. He applied it to the Stark effect.
Which is?
That's the phenomenon where the spectral lines of an atom, the specific colors of light it emits, split into multiple finer lines when you put the atom in an external electric field.
A well-known experimental effect.
Right. So the papers include these really detailed calculations and diagrams. He's comparing his theory's predictions for specific hydrogen lines.
Balmer lines.
Yeah, things like H-alpha, H-beta, H-gamma, H-delta, comparing the predicted splitting pattern and intensities with what was actually observed in experiments.
Okay, the moment of truth. How did it do?
Well, the source is quite candid. It says the agreement is tolerably good for some components of the splitting.
Tolerably good. Not perfect.
Not perfect. It explicitly notes huge differences for other components.
Uh-oh.
Yeah, it mentions things like predicted strength ratios for certain lines being unobserved or questionable compared to experiment. And it indicates these discrepancies actually made Schrödinger himself skeptical.
He admitted the problems.
Right there in the paper, it's quite remarkable, actually. Shows real scientific integrity.
It absolutely does, and it highlights the scientific process perfectly, doesn't it?
How so?
Even a theory as revolutionary and, frankly, beautiful as wave mechanics still has to face the hard facts of experimental data.
No theory gets a free pass.
Exactly. And it's a real testament to the rigor of physics that Schrödinger himself, the guy who invented it, pointed out the inconsistencies.
He didn't try to sweep them under the rug.
No. He flagged them, basically saying, okay, here's where the theory needs more work, or maybe here's where the experiments might need another look. For physicists, that's not failure. It's a signpost pointing towards the next step in understanding.
That's a great perspective. Okay, so while we've focused a lot on the quantization problem and the Stark effect,
Which are central parts for sure.
Schrödinger's collected papers actually cover more ground than just that, right?
Oh, absolutely. It's a collection, after all. The volume also includes important papers on things like the Compton Effect.
Which is about light scattering off electrons.
Right, showing particle-like behavior of light. And also the Energy-Momentum Theorem for material waves.
Exploring fundamental conservation laws in this new wave picture.
Exactly. And another one on the exchange of energy according to wave mechanics.
So he was really trying to build a complete system.
You can see the systematic effort. He wasn't just solving one puzzle, he was trying to construct a whole new framework for mechanics, exploring its implications across a range of different physical phenomena. It really shows the breadth of his vision, even in those early years.
So, stepping back then, what does this all mean for us today? What's the big takeaway from diving into these specific papers?
Well, Schrödinger's collected papers, they genuinely revolutionized physics. There's no other way to put it.
Providing that compelling wave-based alternative.
Exactly. Offering a whole new language, a new conceptual toolkit for understanding the quantum world.
And the core concept, the wave function psi v, that remains absolutely central to quantum mechanics even now, decades later.
It does. Even if our interpretation of what it means has evolved and continues to be debated.
Right, the measurement problem and all that.
The mathematical object itself, the wave function governed by Schrödinger's equation, is still the bedrock. This volume really captures that incredibly exciting, fertile, maybe slightly uncertain period when quantum theory was being forged.
You feel like you're watching them grapple with the very fabric of reality.
You really do.
Yeah.
And it offers, I think, an important reflection for us.
Which is?
How do we appreciate the sheer monumental impact of these early works,
Yeah.
while also recognizing the humility, the self-awareness of the scientists themselves, like Schrödinger admitting upfront that his theory wasn't yet conclusive.
Knowing it was still a work in progress.
Exactly. It's such a powerful lesson in the ongoing nature of science. Even the biggest breakthroughs often start incomplete, and the quest for truly conclusive answers can be long and winding.
Yeah.
It pushes us to keep questioning, keep refining.
And that brings us pretty much to the end of our deep dive into Schrödinger's collected papers on wave mechanics. What an incredible journey, really, seeing how a physicist wrestled with these fundamental questions.
Truly mind-bending stuff, even today.
Yeah. And if this deep dive has maybe sparked your own curiosity, just think about how these fundamental, almost abstract ideas we talked about, proper values, wave functions, wave-particle duality, how they actually underpin so much of the technology and the scientific understanding that we just take for granted today.
From lasers to semiconductors to modern chemistry.
It all has roots right back here. These are the deep foundations of our modern world.
It really makes you wonder, doesn't it? In a world that often wants instant answers, quick fixes.
Yeah, everything now, now, now.
How can we cultivate that patience, that critical thinking needed to really engage with complex, evolving ideas, like Schrödinger did when he faced the, quote, impossibility of a final definitive theory right at the start?
That ability to sit with uncertainty and keep working.
Precisely.
Yeah.
It's a skill maybe we need now more than ever.
A really thought-provoking point to end on. So we invite you, our listeners, to continue your own deep dive into this fascinating world. What unexpected connections or maybe aha moments did you uncover listening to this exploration?